Great. So hi, everyone. I'm Markus Baumann. I'm a senior data scientist and project lead in the business area Artificial Intelligence at MHP. For those of you who don't know MHP, we are an IT and management consultancy and a subsidiary of Porsche. We are focusing mainly on the automotive industry, so manufacturers, suppliers, dealers, and importers. And we also transfer the strategic innovation from the sector to other industries. And today, I'm happy to talk to you about digital twins and why I believe that they are a key enabler for the trends and challenges we are facing today. I will discuss our approach to bring digital twins scalable to the cloud, to speed up development and deployment. So when talking to our customers in automotive, we are seeing a combination of trends and challenges emerged in recent years. Examples include autonomous driving and electromobility. But also that software now is seen as a revenue generator, and this results in a new situation that cannot be addressed like in the past. And we think that there's a need for a new perspective, as we cannot do research and development like we used to, and we are faced with some obstacles like messy data, that development times are getting faster and faster. We are faced with new technology, new needs. Think about environmentally friendly mobility. We have little to no experience and also new hazards. So the bottom line, again, the old way, the old over-the-wall thinking, if you will, does not longer fit our needs. And we believe that digital twins, especially when we combine those with AI, offer a new perspective to tackle these challenges. And here I define a digital twin as a living digital representation of a physical system that is dynamically updated to mimic the structure, state, and behavior of that physical system to drive a business outcome. So at the core, there is a model of that mimics the behavior of the physical object. Digital twins became possible in recent years, since today we can see a car as an IoT device. There were 3 key developments that led up to this. First was that sensors were added to the cars, so we generate more and more data. The second thing is that we have more computing power now available both in the car, that is on the edge, so we can do data processing and transformation, and also in the cloud. The third part, connectivity, enables us to collect a lot of data, and this resulted in what we can call data at scale. So we do not have only test vehicles, we have a rich amount of data, but a whole fleet that generates data. And we can use this data to our advantage to build digital twins and to break down, like I said, the over-the-wall thinking we have, so we can, for example, enable a feedback loop back to development and learn from the operations we have. There are, however, some key challenges I want to highlight when we build digital twin. And the first is that we often have custom solutions and require a specialized skill set, that they take a long time to develop. And since we are modeling whole fleets of vehicles, we need to scale to hundreds of thousands of predictive models, and we need to update those predictive models based on operational data. And we believe that by providing templates to our customers, that will help them to bring their models for the digital twin to the cloud, and this helps simplify deployment, reduce costs, and to reduce cost. So when we define such a template, how do we do this? We take a look at what we do to build an updatable digital twin, and this consists of 2 phases. The first one being the model building and calibration, and the second one, the in-production deployment of the digital twin. So we start by using some sort of modeling technique, be that a first principle model, empirical model, or a data-driven approach, or hybrid approaches, and a training data set to build the model. We then perform a sensitivity analysis to know what parameters we should update. Think about the parameters of the model, for example, as the weights and biases of a neural network. Then, using some sort of Bayesian algorithm like an unscented Kalman filter, we do an initial calibration of those parameters and deploy the model in production. There we use the model to predict measured values, and we can compare those predictions to the measurements we get from operational data. We calculate the error, and if the error is below a certain threshold, we do not need to change our model, since it still reflects accurately the state of the physical system. However, if the error is above a certain threshold, we need to update the model parameters to reflect the latest change in operational data. So when we take a look at this, we need 3 things. We need to handle data, do some sort of predictions and updates, and that's exactly of the core of this of how we think about digital twins, and that is we divide a digital twin at its heart in three basic services. That is the data service that allows us to tap into any database we find with the customer and to integrate this platform into a pipeline. Furthermore, we have a prediction service and an update service, and we divide those two, or we use those two, since we then are able to independently scale them. You can imagine that if you remember from the previous slide, at a given point in time, we have more predictions than updates. So this gives us flexibility. Also, we model complex systems by dividing it into components. So when you model an EV, think about combining the driver of that EV and a battery twin to model the whole electric vehicle. And we can model aero engines by combining the inlet, compressor, combustion chamber, turbine, and nozzle. And to show how to apply this template, we built a showcase, and we deployed this showcase to AWS using AWS Fargate. Here on the bottom, you still see the three services. We have here a time stream database that collects the measurement and an Amazon DynamoDB database to store the model's parameters. This is because we have, of course, for every twin different parameters, so we need to be able to store them. Important to note that the showcase and the data there I'm showing shortly is synthetic data we used because we want to be able to show, for example, to speed up the degradation process of the battery. So, as I said, we wanted to predict the state of health of the battery. Use case is, I think, because we want to, the state of health of a battery is a direct indicator of the remaining value of an electric vehicle. If we take a look at the video I'm showing, you can see here now an overview of a small fleet, and I can display a more detailed view of a twin. And on the bottom right corner, you see a battery check date, which updates as we have as new measurements become available to us. So, and this is one thing I want to highlight here too, is that using updatable digital twins, we can reflect change in the physical system as it ages. And here, for example, we update the date for the battery, when the battery check should be due. If we do not have an updatable model, this prediction would stay the same, even though as the model ages over time. So to summarize, I hope I've given you a good overview why digital twins offer a new perspective for us, that we can reduce costs and simplify deployment by developing templates, and that the digital twin approach is updatable. We can scale it through its modular structure, and it enables sustainable development because we can easily add functionality because we have this very modular structure. And with that, I'd like to thank you very much for your attention.
Markus, our next question is for you, please, is what level of components does the twin go down to? Does the twin then follow the products as provenance tracking tokens? Will these tokens become available to end of life users, reuse and recycling?
Mm-hmm. So in this showcase, we are at the battery level, but you can, through the modular structure, of course, divide the battery again into until you get to the individual cell. And of course, the digital twin should follow the whole life of the battery, if you will, and therefore the use case recycling, reuse, second life is something we, of course, want to be able to enable using these twins. I hope this answers the question.
Thank you. And the next question again, Markus, for yourself is, does your digital twin use a 4D ontology?
Not right now, no.
Markus, what platform is your digital twin built on?
So we've built this on AWS and deployed this using AWS Fargate for the showcase.
And the linked question here, which has come up in a few of the other questions as well, is do you think the templates could be used in other verticals other than automotive? For example, trains, aviation, other transportation methods?
Sure, of course. Basically, we try to frame it as general as possible, so we can use it and apply it in other verticals.
Markus, next question for yourself. Do you take a take data from individual battery cells and use machine learning to learn how cells degrade in response to use and abuse?
So for this showcase, we, as I said before, we are on a battery level. Goal of this showcase was to apply the template and show what we can do with the template. So we did not go down to battery cell level for the modeling.
Very good. And the final one here is, who is the customer of this digital twin model? The fleet manager, car manufacturer, or car owners?
Okay, so for this showcase, this would be something the fleet manager and also the car manufacturer can use. Mainly, however, that's fleet analytics and predictions.